here. Okay, guys, so let's start. So good afternoon, everybody. So last time I started to explain analysis of clocked sequential circuits. Okay. So first of all, what do you mean by analysis? What the word analysis here means? Very simple, very simple. It means I want to find the relation between the output of the circuit, input of the circuit. That's it. This is similar to the truth table we had before. So in case of combining, so I want to do something similar to what we did before in combinational circuit, like truth table, right? So you remember, in case of combinational, okay, to describe the relation between the input and the output, we created truth table. So is that true? So we have X, Y, Z, and then I put all possible cases here, and then we have F. So this table can make the relation between input and output. Is that okay? I want to do the same thing here, but for sequential circuits. Truth table is not going to work. Why? Because truth table gives you the relation between input and output. But in case of sequential, the relation between output, not only input, but also the state or the values of the flip-flop as well. You got what I'm saying? So that's why I think one of the questions you have the coming lab, what is the difference between truth table and state table? Okay. So actually here state table is actually describing the relation between output, okay, and is describing the value of the output of the circuit, but in sequential circuits. So it's exactly similar to the truth table, but truth table is used in case of combinational. State table is used in case of sequential circuits. One more difference: in truth table, the output only depends on the inputs. Here in the state table, as you will see, or as already explained last time, the output not only depends on the input, but also the current state. What do you mean by the current state? I mean the value of the flip-flops. Okay. So I have here 4 examples. Okay. Last time I explained the first example here. They are the same. And in this lab, you are going to have also one something like that, but it's very simple. So if you can understand one of them, all of them are the same way. Okay. That's why I'm going to go through these 4 examples. So this is an example for sequential circuits. Any sequential circuit must have flip-flops. Okay. Sometimes it has some combinational circuits, as we see here. Some combinational circuit. Is that okay? So as you will see in these examples here, it's not always you are going to have combinational circuits here, okay? But all the time you should have, in case of sequential, you have flip-flops. So as you see here, and because this is synchronous or clocked, all of them have the same clock. All the flip-flops are connected to the same clock. That's why they are synchronized. They change at the same time. Okay. So as you see here in this circuit, you have 2 flip-flops, as you see here, and because every flip-flop, as you know, is going to store 1 bit. So how many states you can have? How many states? Okay. For sure, in case of I have 2 bits for the 2 flip-flop. In this case, I can have up to 2 to the power of 2. Okay. States, okay, so which are actually 0, 0. So for example, I'm going to assume this is flip-flop A, flip-flop B. I'm going to assume this is A and this is B. So actually it can be 0, 0, it can be 0, 1, it can be 1, 0, it can be 1, 1. Okay, so these are 4 states we have, okay, based on the values stored in these flip-flops. Okay, why you are saying up to? Very important, because sometimes I'm going to use all states. Sometimes I'm not going to use all of them. So here I have 4 states, but actually the circuit is not going to use the last state. That's why I'm saying up to. You got what I'm saying? Anyway, so this is the meaning of states. And in each clock, this transition happens. Transition. What do you mean transition happens? It means if I'm in this state and there is a clock, based on the values of the inputs, I may stay in the same state. Or I can move to this state or with this state and so on. Transition happens at the clock based on the value of the input. You get what I'm saying? That is why it's after I create this table, I'm going to tell you how this is the state table. I can draw what we call a state diagram. Okay. So in this state, both of them are the same. Both of them are giving the same information, but this one in a visual way. This one like in a table, but both of them are the same. What is this? I'm going to tell you what is this. Okay. This is what we call a state diagram. So the state diagram here, these are all the states we have. So two flip-flops, they can be 0, 0, 1, 0, 1, 1, 0, 1, and so on. This is all the states we have, okay? And then we can see transition. Maybe if I'm here, I'm gonna come to here, transition. Or if I'm here, I'm gonna come to here, okay? If I'm here, maybe I'm gonna stay here. This transitions happens at the clock. So every time there is a clock, transition happens, okay? So, and actually it depends on the value of the input, which is X. I'm going to give you more details, but at least you should understand for now, we have what we call states. You should understand transition, what transition means, and it happens at the clock. Okay. So for example, if for sure, I'm going to explain how, if you have this one, how can you make this one? That's easy. But for now, I just want to explain to you how the circuit works. We have states, every clock you move. Based on what? Based on the value of the input. For example, here, the first number we have here, this is the input of the circuit, which is X. So what this diagram is telling me is, if I'm in state 0 and X is 0, so next time I will be here. When the clock comes, I will be here. You get what I'm saying? As long as X is 0, I'm going to continue here. Every clock in this state, another clock in this state, another clock in this state, as long as X is 0, okay? If X is 1, and that's what's given to me here, if X is 1 here, that means I'm going to move from this state to this state here. Okay. Now, I can repeat again. For example, if I am in this state here, okay, and X is 0, so I'm going to come back to here. Okay. If X is 1, I'm going to come to here. This is what it's telling me. So based on the value of X, every time there is a clock, transition happens. Okay. So I'm going to give you again, don't worry, I'm going to explain, but I just want you to understand how the circuit works. That's it. So I'm going to show you how we get this table, and then from this table, how can we make the state diagram? And you should understand both of these two are exactly the same thing. They are giving the same information, but in a different way. So if I give you this one, you can make this one. If I give you this one, you can make this one. Is that okay? So let me go back here. So this is the meaning we have states in clock. Every clock we change the state. Also, if you look at this circuit, we have input here. This is the input X. Okay. So, and also we have output coming from here. Okay. So the first thing we are going to do right now, how can we make a state table? The state table. The state table should tell you what? Given the current, so let me show here. Yeah, so this is the state table. So the state table is telling you, given the current state or the present state for A and B, for flip-flop A and flip-flop B, and given the value of the input, okay? So this is you can consider it like this is the input, okay? So given these inputs, what should be, what is the output, and what is the next state? Okay, so the part here is going to confuse you for sure is this input at time t, this output at time t, this next state is actually at time t plus 1. I'm sure this confuses you, so pay attention to this part, okay? So what this means? It means this one before the clock comes. So if you have a clock, for example here, so this is time t. Once the clock comes and the transition happens, this is at time t plus 1. You get what I'm saying? So I'm giving you the value before the clock, and I'm telling you what happens after the clock comes. So before the clock, A is 0, B is 0, X is 0, and Y is 0 before the clock. When the clock comes, okay, we're gonna, A and B will stay 0, 0. So I'm gonna stay in the same state because X is 0. You got what I'm saying? Now, it is 0, 0, but X is 1. Assume X is 1, okay? If X is 1, so in this case, that means this is the current state before the clock comes, okay? Y is 0. But when the clock comes, the flip-flop are gonna become 0, 1. So again, you should understand what I mean by at time t or at the current time, you understand what it means at time t plus 1 after the clock comes. Okay. So anyway, very simple. So now, given what I want to explain right now, guys, two very simple things. Again, let me tell you what I explained. I hope based on what I explained, number one, you should understand what is sequential circuit. Okay. I told you sequential circuit should have at least flip-flops. It may have some combinational circuit like this one. Sometimes it does not. Okay. Also, it's number one. Number two, given what I'm going to explain right now is given this circuit, how can you create something like the truth table? It's not a truth table. Okay, it's a state table. Okay, but it is equivalent to the truth table we did before. Okay. And this number one. So given this one, how can you make this one? This is number one. Number two, given the table, how can we make the state diagram? That's it. And then we are done. Okay. So this table can describe the relation between input and. So the way you have to do it, guys, is number one, you need to calculate. We have here several equations you need to calculate. The first equation, we call it a characteristic equation. Characteristic, you don't need to calculate the characteristic equation, you just need to know it. So the characteristic equation giving you the relation for a flip-flop, the relation between output and the input. Okay? And as you know, in case of D flip-flop, Q is equal to D. Q at time t plus 1, when the clock comes, that's why it is this way. Q at time t plus 1 is equal to D at time t. You understand what I'm saying? Because this is how the D flip-flop is working. Whatever you have here, when the clock comes, it's going to move to here. This is what we call characteristic equation. Okay. So in order to calculate, this is a very easy case because actually the output here is equal to the input. Okay. When the clock comes. So in order to calculate the next state, all what I need to calculate is the current value for D. That's it. I need to know what is the value of D. That's it. And this is actually represented by what we call a state equation. So the state equation gives you what is the new value for A and B, what is the new value for the flip-flops here, okay? Given the current value for A, the current value for B, the current value for X, okay? For A and B. And in this case, it is easy because this one is D flip-flop. So these values are actually the input we have here. So if you look at the input we have here, okay, so this one is actually A, this one is actually X, this one is X, this one is coming from B. Okay, so this one actually XB, this is AX, so this one here is actually AX or BX. Okay, as I told you also last time, because always this part at time t, always this part at time t, always the output equation for Y here, it's so here the output equation is actually just, so here this one is actually B, this one here is actually A, okay, this one is actually X, so this one is X prime, this one A or B, okay, so actually Y here is equal to A or B, X prime, okay, very simple. So what I told you, what usually we do is, because everything here in the output equation is always at time t. So you just to make it think it's easier, we just cancel the t. So that's why you are gonna write the output equation this way. I'm gonna say y equal. So every time you don't see time, that means it's at time t plus 1. Okay. Same thing here, because this one always at time t. Okay. So I'm gonna cancel just the t. Same thing here. Okay. So that's why now the equation I have is, these are the equations I have. The next value for the flip-flop A, okay, the next value is equal to AX plus BX or BX. You got what I'm saying? So again, the first thing you have to do, you have to find the input here, you have to find the input here, and you have to find the Y here. That's very easy, right? This is you have to create this equation. Number two, this is a very easy case here because Actually, I need to get the next value here. Okay, but this is an easy case because once you know the input here at time t is actually going to equal to the next value here for A, because this is D flip-flop. This is not going to be in the same case in the if I use other flip-flops. Okay, but anyway, let's stay here. Okay, once you have this one, all what I'm going to do here, guys, is this is the truth table. So I have AB for the flip-flops, and then I have X. Then I'm going to write here all possible values as we did before. Okay, so just write here all different combinations. Okay, like here 4 zeros, 4 ones, 2 zeros, 2 ones, and so on, 0 1 0 1, and so on. So okay, and then you need to calculate this part. Very easy. So all the flip-flops you have to put them here. All the inputs you have. In this example, I have one input. In some examples, I may not have any inputs. That's okay. In one example, you have only one flip-flop, and this is the case for your lab. Or sometimes I have 2, sometimes I have 3. Whatever the number of flip-flops you have to put them here, input here, put all possible cases, and then you need to calculate these ones. That's it. Very easy. Okay. So remember, all of these are at time t. At time t. So let's start with y. For example, how can I calculate y? Very easy. I already found the relation for y. So as you see here in the table in here, I'm gonna just point at this one because you may not see this one. Okay. So y, I told you are gonna cancel time t because it's always at time t. Okay. So the output y at time t, not t plus 1. So I need to calculate the current y before the clock comes, not the next y. Okay. So here y is equal A or B and X prime. So that's what I'm going to do for every record. So for every row here, I'm going to see I have, so y is equal X prime and A or B. Okay, so I have here A, I have here B, I have X prime. So I'm going to calculate the value of y for every record here based on this equation. Very easy. Makes sense? So if this is the current A, current B, current X, so this is the current Y or the present Y before the clock comes. Is that okay? Now, what is the next state for A and B? Okay, this is exactly the state equation. So if you go to the state equation here, this state equation is actually describing the next A given the current A and T. Remember this part? This part here is the current A and T. Okay. So all what I'm gonna do again, I'm gonna just use this equation. So for A here, for A the equation is AX or BX. So here I'm gonna use AX or BX. That's it. So for every record here, I have ABX. So I'm gonna apply here in this equation, then calculate one by one here. Is that okay? Same thing, I already found equation for this one. The equation for this one is A prime X. So this one, A prime X. Okay. So all what you have to do again, you have here X, you have here A. So you have to calculate A prime and X. Give you this one for every record. Okay. So once you do that, I am done. I got the state table. Any question? Again, guys, I gave you 4 examples. I'm gonna follow the same steps. Everything is just the same. So that's why if you understand one, all of them are the same. Okay. And the coming lab, you are gonna do one circuit. Okay. Any questions? Okay, good. So now, okay. So now I created what we call a state table. A state table gives you the relation between, this is the current values for flip-flops and for input, okay? And this is the next state or next value for the flip-flop given this input and given the current value and input, and this is the value of or current value of Y, okay? So this is enough. This is like a truth table. So this is enough to understand how the circuit works. This one gives you all the information you need to understand how the circuit works. Is that okay? That's okay. But actually, sometimes it's sometimes I wanna represent this table in a visual way. That's why this one does not give you new information. Just I'm gonna represent the same information here, just in a visual way. Okay. Sometimes this one may be easier for me to understand how it works, whatever, but both of them are the same. So if you have this one, you can mix this one. If you have this one, you can mix this one. So now I'm going to explain what I'm going to explain now. Given the table, once you created the table, how can you use the state table to create what we call a state diagram? And that's it. Okay. So let's see how I'm gonna do it. So let's I'm gonna, okay. So okay, I want to do it by myself here. I'm gonna just put this one as a reference here. Okay. Or okay, let me put it up here, for example. I'm gonna remove this one for now. Okay. So now I'm gonna show how I will do it. Okay. Look here, guys. It's very simple. How many states you have? I have 4 states. For every state, you have to make a circle. Very easy. So what I'm gonna do right now is I'm gonna make a circle here for 0, 0, state 0, 0. And then I have state 0, 1, and then I have a state 1, 0, and then I have a state 1, 1. Is that okay? For all cases you have. Okay. Is that okay? So you can see you can get from the table here. This is the state I have. Okay. Sometimes I don't use all the states. Now I have 2 flip-flops. I have 4 states. Here, in this example, I use all of them. Sometimes it's not the case. But anyway, so this is number 1. Number 2, now I'm going to go to the table, and then based on the value, look here. Every arrow here is a transition. When the clock comes, what's going to happen? Given the current state and given the current input. So this is input, and this is y, x and y. Okay, so remember, this is x and y. So let's see how I can get this information from the table. Very easy. Look here from the table. First of all, you can see the state 0, 0. It has two transitions. 2 transition. One transition when x equals 0, one transition when x equal to 1. Okay. Same thing for state 0, 1. It has 2 transitions. Same thing for the state 1, 0. Same thing for state 1, 1. Let's start with the first one. So let's take one by one. Let's look at this record here. Okay. Can I remove everything? So let's look at this one first here. Okay. What this one is telling me? This one is telling me if the current state is 0, 0, x is 0, so the next one is 0, 0, and y is 0. That's what's telling me. So how I can do it in the table here? Okay. So here I'm going to do something like that. If I'm at 0, 0, and x is 0, y is 0. So I'm going to do this way. Very easy, right? So what this one is telling me, if you are at 0, so this row here is represented by this arrow this way. Very easy, right? So if I'm in state 0, 0, x is 0, I'm going to stay in this state, and y is 0. Current y, not the future, current y, okay, is 0. Okay, so now I finished the first row here. Let's go to the second one. The second one is telling me if you are in state 0, 0, and x is 1, the next state is 0, 1. So here, so if I'm 0, 0, I'm going to go to 0, 1. That's what's telling me, right? Where x is 1 and y is 0. Y here is 0. Is that okay? I am done with the first state here. I can do the same thing with the other states, because these two, when you are in state 0, 0. These 2 when you are in state 0, 1, and so on. Is that okay? So now I'm going to move to here to this state. I'm done with this part here. So every row is going to be 1 transition. Okay. So if you look at this one, I'm telling you, let's start with the first one here. If you are at state 0, 1, which is this one here, 0, 1, okay, and x is 0, your next state is going to be 0, 0. Is that right? I think something is wrong here. I need to correct it. I think something is wrong here. I got this one from the textbook, but I think this is not true. If you are in 0, 1, oh, sorry, I'm sorry. Yeah, I just flipped it. 0, 1 is here. I think I made a mistake. Yeah, 0, 1. Yeah, I think I made a mistake. Sorry. So just because I wanna, it's okay to make this way. It's not wrong. It's okay, right? It's okay to put the state this way. It's the same. But just because I want to follow this one here, I don't want to confuse you by flipping some of them. But it's still okay. It's still okay. So what I did here, this is 0, 1. I put it here instead of here. Okay, instead of here. So anyway, so it's still okay. But all what I'm gonna do here, I'm gonna just here after. It's whatever the order. It's not gonna make a difference. It's giving the same information, but I just want to follow this one just to show you how can we make it. So don't worry about the order. You understand what I'm saying? So here, for example, I'm gonna use here 0, 0, 0, 1. Here I'm gonna just use this one. Okay. Again, guys, you don't need to follow the exact, I just want to follow what I did here or what the textbook did here, but there is no specific order. Whatever you do is okay. So what happens here, this one has to come to here, and this is 1 and 0. Is that okay? So now let's come to the next one here. When the input is 0, 1, which is this case here, okay? When it is 0, 1, and when x is 0, so I'm gonna go to state 0, 0. Okay, so that means you are telling me this row here, I'm talking about this row. This row here is telling me if you are at 0, 1, you are gonna go back to 0, 0. That's for this state to this state when x is 0 and y is 1. Is that okay? Don't worry about the order of them. It doesn't matter, because you think about it, it's going to give you the same information. But I just want to follow the same thing I did here, okay? So you see, this is one transition. Let's look at the next transition here. Next row. Here, this one. So this one is telling me if you are at state 0, 1, you are going to go to 1, 1 when x is 1. So here, that's why I'm going to go this way. Okay? Yeah, as you see here, when 1 and 0. And you can see for every state, there are 2 transitions out of every state, because every state has two rows here. Is that okay? So let's move to the next one here. 1, 0. Okay. So 1, 0 here. Again, if you are at 1, 0, you are going to go to 0, 0. You are going to go to 0, 0. Is that okay? When x is 0 and y is 1. Okay. Any questions? Very easy to translate, to move from this one. You can draw this one. Is that okay? So for every state, you can see every state has two transitions to the, sometimes to the same state or to other states. Okay, based on the value of x and y. 2, 2, 2. That's why you can see here for every state there are two getting out, 2 transitions, either here or here. Why? Because we have only one x. If x is 0, I'm going to move this way. If it is 1, I'm going to move this way. You got what I'm saying? Let's have more examples just to understand better this one. This is nothing is new here. I'm just explaining to you what I have just explained right now. These 2 records, because of these two rows, you can have 1 here and 1 here. Okay, because of these two rows, I can have 1 here and I can have 1 here. Okay, I just use color to just explain what I have just. These 2 rows are going to give me this transition and this transition and so on. Okay. Sometimes what I want to tell you here in this slide, okay, so what I did right now, guys, is number 1, given a circuit, you should be able to calculate a state table. Okay. Given a state table, you should be able to draw the state diagram. Is that okay? However, in the textbook is telling you it may be easier. It may not, because what I did, I just used the state table just to move from here to here directly. And it was easy for me. It was not difficult. But just I want to tell you, sometimes you don't need, sometimes it may be easier to restructure or reformat this table to create table like this one. So this is nothing is new. I just reformatted or reformatted or restructure this one. Okay. So how this one looks like. So as you see here, this is the current state. Okay, for A and B. This is the next state in 2 cases, when x is 0, when x is 1, right? And this is the output in case of x is 0, x1. So actually what I did here, just to make it easy, these 2 rows are actually represented just in 1 row here. How? I'm going to tell you how. So here, what I'm saying, let's look when x is 0 here, which actually, so here, if the current state 0, 0, okay, which is the case for these 2 rows. Okay, when x is 0, which is the first row here, x is 0, so A and B should be 0, 0, and this is the case here when x is 0. Okay, y is 0, which is this one here. So all what I did here, guys, is just the first row is the first row here is I just represented here in x of 0, y of 0 this way. Sorry, x is 0 here as well for y. And this for the next. So again, you may not even need this one. I think it's not difficult to move from here to here directly. I'm not going to examine anything. I'm not going to ask you, but maybe anyway. So in the textbook, it's telling you if you have this one, it may be easier to use this one. But again, this one is nothing is new. So here, it just, if the two rows here are represented in one row here, because if you see here, in these two rows, it's the same 0 and 0. That's why it has 0 and 0 here, okay? Also, you can see x is 0, x is 1. That's why here, x is 0, I'm gonna put it here for these two, right? X is 1, I'm gonna put it here. X is 0 for y, x is 1 here. That's why one row here is represented by 2 here. Same thing here for this one row here is represented by 2 here, and so on. Anyway, you may not need it. You can just move from here to here directly. Just I restructured it. That's it. Any questions? Okay. So let's explain this. It's a second example, which is very close to your lab. So in the current lab, you are going to implement the same circuit here, but I made it easier. Okay. So let's look at this one here. Here you have only one flip-flop, as we see here. Okay. The input here is coming from this XOR and another XOR here. So you have, when you have two inputs, as you see here, we have two inputs, X and Y. Is that okay? In the current lab, I made it easier. So it's exactly very close to this one, but I just cancel this one and you have only one input X. Just make it easier. Got what I'm saying? So let's see how this one works. So this time you have two inputs, you have only one flip-flop, because so how can we do this one? Very easy, very simple. Look here. Number one, similar to what I explained before, the characteristic equation, because this is D flip-flop, the characteristic equation, the output is equal to D. The output here at time t plus 1 equals the input here at time t. Okay. So all what I'm gonna do, I need to get what is the value here, because this value will be the state equation, will be the output here. So the output here is equal to D of A at time t. Okay. And this one, actually, you have here A, you have here AX XOR Y. So this one actually becomes X XOR Y XOR A here at D. And this value here at time t is going to be this value at time t plus 1, because this is D flip-flop. Okay. So let's see how I can make this table very easy. First, what is input you have? So here, as I told you before, you need to put all flip-flops you have. You have only one flip-flop. You need to put all inputs you have. That's it. And then you have to put all possible cases here. So this part, you have to fill up this part with all possible cases. 0, 0, 1, 0. So all possible cases. This number one. Number two, again, I'm just repeating what I said before, because it's you need to use the same steps. It's the same steps. Okay, anyway. Then I need to calculate this one. This one is the next state. We don't have Y, we don't have output. And usually, if you don't have output coming from combinational circuit, in this case, is there a circuit that doesn't have output? Okay, let me clarify this point. Sometimes we take the output from flip-flops. Sometimes we take the output from a combinational circuit similar to what I did before. So here, what I did here before, I got the output from a combinational circuit this way. Just to differentiate between them, I'm gonna call this one output, but I'm gonna call this one states, okay, or the flip-flops. So usually in practice, if you don't have this one, so usually I'm gonna take the output from here, but I'm not gonna call it output. Otherwise, we are gonna be confused between this one and between when you take it from the flip-flop. So usually when there is no output from a combinational circuit, that there is no circuit that doesn't have output, right? So actually the output will be taken from A and B. You understand what I'm saying? So this is the case here. So the case here, although there is no output in the sense of that we don't have like something like Y, so actually this will be the output of the circuit, but we will be careful to call it output, okay? Otherwise I'll be confused between the output coming from a combinational circuit and the state here. Anyway, so now, given these values, how I can calculate A, the next state? Very simple. You have this equation here. Very simple. So here, the new state for A, and this is the new state for A, is actually equal all these values XOR together. That's it. So all what you have to do for every row here, you have to use this equation. Okay. So here, if you want to do it, 0 and 0. You know, if you want to do this XOR, you have to do it in your two steps. Okay. 0 XOR is 0. What is the value of this one? If they are same, so XORs give you 0. Okay, so the result is 0, right? Same thing. 0 XOR 0 is 0. Okay, let's see another record. This one here. Okay, so here we have 0 XOR 0. This is how XOR works. When they are equal, you get 0. Now 0 XOR 1. When it's different, you get 1. Okay. Anyway, so you need to go step by step, calculate based on the current value for A, the current value for X, the current value for Y. You can calculate the next step. That's it. I'm done. I just created the table. Okay. Let's now, given this table, how can we draw the state diagram? Okay. That's what I'm gonna explain now. Okay. Again, I'm gonna So I'm gonna try to do it by myself. So as you see here, we have only one flip-flop. So that's why I'm gonna have two states. One is at 0, one is 1, right? Because it's only one flip-flop. And now let's see how it works here. Look here, for example, what this one is telling me. What this one is telling me, if you are in state 0, you are gonna stay at state 0, okay? When the two inputs here are 0, 0. So what I'm gonna do here, I'm gonna do something like that. I'm gonna say 0, 0. So that these two inputs are actually representing X and Y. Okay, so this row here is telling me if you're in state 0 and X and Y 0, 0 are gonna stay at 0. Yeah. Let's look at the next one here. Okay. The next one here, is telling me, okay, if you are in state 0, you are gonna go to state 1. So I'm gonna come here, okay. When the input is 0, 1, so I'm gonna say 0, 1. Okay, because I have two inputs here, not one. Don't be confused. This is a very simple thing. Because before I just hear the input, before I put a slash here, and this is the input and this is the output. I'm not gonna use a slash this time because I don't have output. Okay, but for the input here, I used only 1 bit for input because I had only one X, only X. This time I'm gonna use 2 bits for input because I have X, Y. Okay, so yeah, so this way. Okay, let's go to the table again. Let's look at the next one here again. Okay, if you are at 0, you are gonna go to 1 in case of 1, 0. So there is another case here. So I'm gonna say comma 1, 0. So that means in these two inputs, if X and Y equal 0, 1, I'm gonna move from here to here, or if it is 1, 0, I'm gonna move from here to here. Is that easy? Yeah. Again, you should continue this way until the end. You will draw this one. So what this one means, it means if you are state 0, you are gonna stay at state 0 at these two inputs when XY 0, 0 or XY 1, 1. Okay. So everyone here is representing one row. So this row is actually this one here, and this row here, you are at 0. You are gonna stay at 0 when XY 1, 1. So it's representing this one. Any questions? Okay. Let's move to the next one here. Now, I'm gonna move to a next one like JK flip-flop. Okay. How it would be different? Again, everything is the same. However, there is a small difference. What is the small difference? It's the small difference is to calculate the new state. In case of D flip-flop, it was enough to calculate the input here. Once I have the input, it is the same, equal to this one. Because this is how D flip-flop works, right? Q is equal to D, right? But now this is not the case now. This is not the case, right? Because in JK flip-flop, the output does not equal the input, right? However, there is a characteristic equation. So this characteristic equation, this is the only difference. So we have a characteristic equation. If you go back to the slides of JK flip-flop, I told you JK flip-flop is equivalent to all of that. So this is, if I have D flip-flop, I'm gonna add this part here to create JK flip-flop. And the characteristic equation that gives the relation between the output and the input, which is JK in this case, this is the characteristic equation. That means the new state is equal to J, the current value for J, the current value for Q prime, or so this part, this is the new state, okay? But this is at time T. This characteristic equation was easy in D flip-flop because in case of D flip-flop, Q of T plus 1 equal D at time T. So all what I have to do just to calculate D, and that's it. Now, if you want to calculate the characteristic equation, you have to calculate the input of J, you have to calculate the input of K, and you have to apply for this equation to get the new state. You understand the difference? Okay. Actually, it's the same thing I did here. I calculated the input of D and just plug in this equation. But here it's easy because Q is equal to D. But here it's not. Okay. This is exactly what I'm gonna do. Nothing is new. Exactly. So again here, guys, in this circuit, you see, number one, I have two flip-flops. So that means I have two bits, right? So how many states you can have? Up to 2 to the power of 2, which equal 4 states. Okay. So now I have up to 4 states. Okay. One more thing here, you can see we have only one input here. We don't have output. And in case we don't have output, actually the output will come from A and B, but we don't have output here. We don't have, to be more accurate, we don't have output coming from combinational circuit, to be more accurate. Okay. So how can we work with this one? Very simple, very, very simple. Number one, you need to calculate what is J, what is K, what is J, what is K. Number two, just plug in here to get the state equation. That's it. Everything else is the same. Okay. So let's see. For example, because we have two flip-flops, please, in exams, in quizzes, don't confuse me. Just to be very specific, because we have two flip-flops, you can just tell me J. You can, because I will. Do you mean this J or this J? Right. So to differentiate between them, for this one, I'm gonna say J subscript A, K subscript A, J subscript B, K subscript B. For the output here, I'm not going to use Q. I'm just going to use A and B, just to make it easy. If you want to use QA, QB, I'm okay, but just to make it easy, just A and B. Okay? So please don't say J, because J, I will be confused. Which J do you mean? Anyway, so let's start with this one. So what is the value of G here? Let's see. The value of G here is equal to B. Oh, that's easy. So this one is AB. Okay? So the first thing you have to do, you have to calculate the inputs. So G of A is equal to B. Okay. And now let's look at K here. JK. JK here is coming from this end. This end has here B and it has here X prime. So actually this one X prime B. Is that okay? So these are the current value for J and K. Okay. And then same thing here. This J is actually X prime. This K here, which is K of P here, is actually is A XOR with X. A XOR X. Okay. Guys, I want to help you in exams, in anything. Every step, even if you don't completely solve the problem completely, every step is doing, I'm going to give you points for that, right? So number one, step number one, you have to calculate the input of the flip-flop. You are going to get some points for this one. So you need to do it, okay? So that's it. That's all what I did, as you see here. So first step here, I need to determine the input here. Is that okay? Step number two, I'm gonna use this input to plug in the characteristic equation. This is the characteristic equation. So you have here J. For J, in the two cases, I have GA and JB. For Q here means A or B, right? So I'm gonna call it A or B. Here or A or B. For K, I'm gonna have KA and KB. Okay. So given what we have right now, you can just plug in, as you see here. All what I did, I just plug in here, and by this way, I got the state equation. I hope you understand why this time it's a little bit complicated than last time. Last time it is D flip-flop. Output is equal to the input. I'm done. Here it is not. You need to calculate the input J and K. You need to plug in this one to get the output. Okay. So by this way, I didn't do anything. I just plug in here, plug in the values of J and K here and here. By this way, I calculated the state equation for A and B. Is that okay? Now, let's create the state table. How we can create the state table? I'm going to tell you. Look here. Similar to what we did before, you have to put all flip-flops you have here, A, B, and you have to put the input here. Okay. Is that okay? Forget this part for now. Okay. So now, and then put all possible cases. Okay. Even in exams, if you do this step, if you show me this step, you are going to get point on this one. And this is something you are going to do all the time. Just put the flip-flops here. If you have two flip-flop, I'm going to put two. You have three, I'm going to put three, whatever. And then I'm going to put input here. We have only one input here. We don't have output, okay? So, and then using this information, I need to calculate the next stage. Is that okay? How we can do that? I'm going to tell you two ways. Listen to me. I'm going to tell you two ways. I'm okay with the two ways. The first way, which is a very straightforward way, is, forget this one for now. The first way is, I already have the characteristic equation. So this characteristic equation is giving me the value of A, given these values, A, B, X. It's already given here. Same thing for B here. This is B, given these values here. So all what I can do in order to calculate these values here and these values here, I'm going to use these two equations. Very simple, straightforward. Is that okay? This is one way to do it. I'm totally fine with that. However, it's okay, but it may be a little bit complicated because look, you have a very big one here. So to apply every record here, put it here, it may take some time, the calculation. It is okay. But maybe there is an easier way. Okay. What is the easier way? The easier way is, for every record here, I'm going to calculate GK, the values of GK, okay, using these equations here. Okay. And then look here. So here, I'm going to using this equation, which are a small equation. This part here is much smaller than this one's, much smaller. So you can calculate GK here. For everyone, you can calculate GK. So given these inputs here, these inputs, you have equation for each one of these one. And they are very easy equations. Some of them, like GA is equal B. So all what you have to do is, GA here is equal to B. So all what you have to do, just copy paste here. Remember, we don't have this one yet. We don't have this one. I want to calculate this one. So given the input you have here, it's very easy to calculate these ones. Again, this is another way. So whatever you do, I'm okay. Okay. So very easy to calculate this value. And then, if you have a flip-flop, you know what is the current value for the flip-flop, and you know the input. Can you calculate the output? For sure, I can. This is what I'm going to do right now. So once you use this equation to have these values here, now I'm going to start calculating this part here. I'm going to show you how. Look here. Again, this nothing is here, okay? So I'm going to calculate it. Look here, guys. Flip-flop A is storing 0, and GK is 0, 0. 0, 0 means what? No change, no change. So that's why this one is 0, is going to continue 0. No change. Is that okay? I'm going to follow the same thing for everyone here. Again, look like this case, 0, 0 means no change. If it is 0, it's going to continue 0, no change. This one, 1, 1, it means it's a toggle. So now if A is 1, so it should become, 0, it should become 1, toggle. Now 1, 0, 1, 0 means it is set. So if it is 0, it should become 1, and so on. So you have the input, you have the Q value for the flip-flop here, and you have the input JK. You can know what is the new value. When the clock comes, what is the new value, which is this one here. So I'm going to use these two, and then I'm going to use A for flip-flop A. I'm going to do the same thing for flip-flop B here, and then this one. Is that difficult? Any questions? Again, I told you have two ways. One way you can do it directly using these two equations. The other way you can calculate the input, and then based on you know how the flip-flop works, you can calculate, because this is given. If you have a flip-flop, you have the current value, you know the Q value for the JK flip-flop, and you know what is the input, the current input. So you can easily know when the clock comes what will be the new Q value. Any questions? Yeah. Any questions? Okay. By this way, I can create the state table. This is the state table here. Given the state table, can I calculate the state diagram? The answer is yes. The state diagram is exactly similar to what I explained before. Now we have two flip-flop. We have 4 states. We have a state 0, 0. We have a state 1, 1. We have a state 0, 1, 1, 0. Okay. Okay, guys. Again, Don't worry about the order. So you see in this example, in the textbook, they put here 0, 0, and then you put 1, 1 here. It doesn't matter. You know why he made this way? Because if you change the order, maybe the figure. If you change the order, maybe it's gonna be, you can see some kind of crossing this way, maybe a little bit complicated, whatever. That's why they put them, but I'm totally fine. They are the same thing. So there is no specific order. You understand what I'm saying, right? I think they selected the order because this is different from what we had before. They selected the order this way just to make the figure looks nice, right? But if you mix them, you are gonna get exactly the same figure, but it's gonna be like there are a lot of crossing, okay? But it's still okay. Okay, there is no specific way. Anyway, so how can I move from this one to this one? Nothing is new. This is exactly as I explained before. So look here, guys. This is a state of 0, 0. Okay, so let's start one by one. Okay, so we have to transition from 0, 0. The first one here, if you are 0, 0 and x is 0, so next time should be 0, 1. Okay, that's exactly what I did here. If you are 0, 0 and x is 0, so here I put only one value, which is x. Okay, I don't have output. Okay, I'm gonna come to here. Let's look at the second one here. If you are in state 0, 0, x is 1, you are gonna stay in 0, 0, and so on. Any question? So these two transition for 0, 0, two transition for 0, 1, two transition for 1, 0, and so on. Any questions? I'm repeating. It's exactly same thing. Okay. Now, any question before I move to the next one? Okay. Let's go to the next one. Again, nothing is new. I'm going to repeat again. Here, I want to give you example on T flip-flop. T flip-flop, okay? The only difference is the characteristic equation. Same thing as I did in GK flip-flop. Same thing as I did in G flip-flop. You need to calculate the input first. Number two, you need to plug in the characteristic equation. This is the characteristic equation of T flip-flop. So T flip-flop is actually the output Q. If you go back to T flip-flop, the output Q is actually equal T XOR Q. You got what I'm saying? This gives you the relation between the new Q value, the new output is equal to T, the input T XOR the current value for Q. So this is at time T, this is at time T plus 1. Is that okay? All what you have to do is exactly similar to what I did right now in JK flip-flop. All what you have to do, you have to calculate T, and given Q, you need to calculate the new state. So this is the new state, given the current state and also the value of T. Okay? So similar to what I did before. So if you look at this circuit, in this circuit, I have two flip-flops, as you see here. This is number one. Number two, I have here one input, as you see here. I have one output, as you see here. The output here is coming from A and B. Is that okay? I have output this way. So let's do it. So again, similar to what we did before, it's just systematic steps, right? You need to calculate the input of the T flip-flop. This is number one, very easy. So if you look here, this is X. And this one is actually B. So actually T of A, please don't say T, please, because I have two of them. You need to tell me which one. So T of A is actually equal BX. Okay, that's very easy. Same thing, you need to calculate this input. So this input is actually equal to X, very trivial. So TB equal to X, very trivial. That okay? What about Y? Y, which is the output equation. I need the output equation Y equal A and B. Very trivial. A and B. Okay. And this is TA and TB. Okay. And now you can calculate the state equation. The state equation is for A is actually equal TA XOR A, which is Q, right? So which is equal BX XOR A, right? Because TA is BX. This is A of T plus 1, just to next state, because this is a state equation. I just plug in here. That's it, very easy, right? Same thing for I have B of T plus 1 should equal TB, which is X, XOR B. Is that okay? That's it. This is the situation. Similar to what I explained before, now you have two options. Either in order to calculate the next state, it may be easy to go for this one, okay? Or you need to calculate these two, and then given A and TA, you can calculate the next state easily, right, from here. Or this is easy, it's not a big one, this is a small one, right? So just XOR, you can do it whatever the way you do it, okay? Okay, that's exactly what I'm explaining here. You need to calculate the output equation, you need to know the characteristic equation, and you need to calculate the state equation. Here, we have two of them. You can keep it this way. You can keep it in XOR as I did here, or you can expand this way. I hate, maybe it's easier because you already know how to make XOR. So it may be this one too complicated, but you already know how to do XOR. So the way I did here, BX XOR, so I can just BX or XOR A and just use this one because I already know how to calculate XOR. I don't need to go down until here. If you just stop here, it should be enough. Okay. Any questions? Okay. So now, given again, here I'm gonna put all flip-flops I have here and the input, and then I'm gonna put all possible cases here. All what I need to calculate, guys, is I need to calculate this part here. I want to calculate this part. Let's start with Y because Y is very trivial. If I go back, this is the output. What is the output equation? The output equation here, A or B. So Y here is equal A or B. All what I'm gonna do here, I'm gonna have A and B, and then I'm gonna do OR. 0 or 0 is 0. 0 or 0 is 0. 0 or 1. What is this? Sorry, and that's why. Okay, is that or and? Oh, this is a mistake. I'm sorry. It has to be an and. So I'm sorry. I'm gonna correct this one. This is and, not or. Okay, please correct it. I'm gonna correct it because if you see here, it's and. Okay, so that's why I got a mistake here. So anyway, so this is A and B. In case of A, so all what you have to do, yeah, you have to do A and B. In case of and, as you know, if you have zeros here, don't think about it. If one input is 0, so I'm gonna have 4 zeros here. Don't think about it. Okay, now I have 2 zeros here. Don't think about it. Another 2 zeros. Now we have 1 1 1 1. That's it. You can easily calculate this part. Okay. Now let's calculate how I can calculate A and B. This is the next one. This is at time t plus 1. How we have equation, right? So let's start. For example, here this one is actually X XOR B. So yeah, you have here X, this is the input, you have B, and then you can do XOR. As you know, in case of XOR, if they are the same, you get 0. That's why here, they are the same, you get 0. They are different, you get 1. Different, you get 1. Same, you get 0, and so on. I'm done with this one, okay? Last one here, this one. I think it's difficult to use this one. I just used what is in the textbook, but it may be because I already know how to make XOR. So it may be easier to use XOR. So I can say BX XOR A. I don't need to expand it. Okay. So this one can be BX XOR A. So you can add one column here for BX because I don't have BX. I have B and I have X, right? So maybe I'm gonna add one column here for BX just to make calculation easy, right? So here, in case of BX, we have 2 zeros. So I'm going to put here 2 zeros because I have 2 zeros here. I have 1 0 here. I'm going to put 0. Then I have here 1, then 0, then 0, 0, 1. Okay, this is BX. Now I'm going to do XOR between BX and A. It's much simpler than using this one. Okay. Anyway, so again, you can see here. Sorry, I'm going to use. Yeah, I'm going to use this is BX. And this is the current value for A. So I have to use this one. And then I'm going to use this one. So I'm going to get just XOR between these two to get this one here. Okay? Let's see it. So here, 0 and 0, they are the same, get 0. 0 and 0, they are the same, get 0. 0 and 0, they are the same, get 0. 0 and 1, I got 1, and so on. Any questions? Same thing as we did before. Once you have this one, you can make the state diagram. Okay. How can you make the state diagram? Again, you have two states, and you have 2 bits. So how many states we have? We have 4 states. These are the 4 states: 0, 0, 0, 1, 1, 1, and 1, 0. Okay, 4 states. And then I'm gonna make transitions. But wait a second. When I make transition, this is the input here. This is input X. We have only one X. Okay. This is AB. This is always here in the state we put AB. But this time, I'm gonna put the output here. The slash is here, the output Y is here. Why? Before we put it here. Why is this time you put it here? It's not a big deal, but I'm gonna tell you why. The reason. So just to differentiate between 2 things, I'm gonna define shortly, right? So again, what I'm saying is that in the previous example, Y, I made a slash and put Y here. In this example, I'm gonna put Y here inside the state. Okay. It's not a big deal. Even in exams, if you make a mistake in this one, I'm not gonna deduct anymore. It's not a big deal. But I made it for a reason. I'm gonna tell you what is the reason. Okay. So anyway, and then after that, everything is the same. So for example, here as you see, if I'm in state 0, 0, I'm gonna stay at state 0 when X is 0 and Y is 0. So what I'm gonna do here, as you see, if I'm in state 0, 0, I'm gonna stay here. Okay, if it is X is 0, and then I'm gonna have 0 here. What output 0? Okay. Same thing here. When it is 0, 0, I'm gonna move to 0, 1 when X is 1. I'm gonna move here. Is that okay, guys? And so on. So everything is the same as before. Again, yeah. They just put the order here in a certain way just to make a nice figure. But again, it's not a big deal. If you just change the order, yes, you will be some crossing, but it's the same thing, the same information. Got what I'm saying? Any questions? Okay. Now, any questions so far? Okay. Now, what I want to explain is that if you have a state like this one, I can represent it using timing diagram. Very easy. You will see right now, because in the coming lab, I'm asking you to do something like that. You will see it's very trivial, very easy. So let's start. You know, there is a transition every clock. So there's a transition here, because this is a rising edge. I hate like very small things that confuse the student. Here in these flip-flops, it's at rising. If it is at falling, everything is the same, but I have to work at falling, not rising. You understand what I'm saying? It's very simple. So that means there is a transition here, transition here, transition here, transition here, transition here. And when I say transition, it doesn't mean I'm going to leave the state because I can make transition to the same state, as I said. Okay. So now let's see. I made it in like animation way. It's very interesting somehow. So here, given the value of X, I'm assuming X is this way. Okay. Because X is going to control how the movement will happen. You got what I'm saying? So if I'm here, who's going to control? If I'm going to come here or go here or here, who's going to control the movement here? Is X, right? Anyway, so I give you X, and then I want to see how it will move. Okay. So originally, I'm in state 0, 0 before the clock comes. So this is at time T. Now, after the clock, it's time T plus 1. Okay. So before the clock, I'm in state 0, 0, and Y is 0. That's okay. So I'm here. Actually, I'm here. Is that okay? Let's see when the clock comes, what's going to happen. Okay, let's see. At this clock, what will happen at this clock? Very easy. Ask the graph. Okay? When X is 1, so at this clock, X is 1. The graph is telling me when X is 1, I'm going to come to here. That means here, I'm going to move to 0, 1. So this one stays 0. This one go up to 1. Make sense? Okay. What about Y? Y is going to stay 0. Yeah, very easy. Is that okay? So this is the new state. What's going to happen here? I'm going to repeat again. I'm going to see what is X and what the graph is telling me. That's why I'm making it like in animation. So that's what I explained first, okay? So this one will stay at Y. This one is 0 and 1. Is that okay? Now, let's repeat again. What's going to happen when this clock comes? Okay, currently I'm in this state here, okay? And X is 1. Because X is 1, I'm going to move from here to here. Okay? I'm going to move from here to here. That means it's going to be 1, 0. So this is going to be 1, and this one is going to become 0. Okay? And Y is 0. That's exactly what I did here. Okay? Let's again, repeat again. If you are here, what will happen? Okay? X is 1. So I'm here. I'm already 1, 0. That means I'm already here. So I'm going to move to this one because X is 1, right? So what's going to happen? So this one should be 1, 1, right? So 1 and, sorry, 1. Makes sense? Very easy, right? What about Y? Y this time is 1. Here. Is that okay, guys? Okay, so I'm going to continue this way here. So you just, as you see, look, based on the value of X, initially I was here. X is 1, so I'm going to move to here. X is 1, I'm going to move to here. X is 1, I'm going to move to here. Okay, now what is X? X is 1, so I'm going to go back to here. Okay, I think now X is 0. Sorry, X is 1, so I'm going to come to here. Now X is 0. Now I'm going to come to the 0 part. X is 0. So X is 0, so I'm going to stay in the same state. Is that okay? Any questions? Okay. So now in this part, I just give you a circuit. I didn't tell you what these circuits are doing because we are practicing. If you have a circuit, how can you calculate the state table? But actually, for this specific circuit, is doing something very useful. Okay? Can anyone guess from the diagram here? Look here, look at the diagram. Assume X is 1 all the time. Okay? Just assume X is 1 all the time. Just I wanna now ignore X. X is 1 all the time. What's gonna happen? Look here. When X is 1 all the time, if I take the output from EB, look at what happens to EB. 0, 0, and then number 1, number 2, number 3, and then go again to 0, 0. Number 1, number 2, number 3. What is this? It is a counter. You are counting 0, 1, 2, 3, 0, 1, 2, 3, and so on. Make sense? Now I want to understand what X is doing. What is the purpose of X? You can look at any time when X is 0. What happens? If I'm here and X is 0, I'm going to stay here. So it's like pausing. You pause it. You stop counting. You stop, pause it, right? So by this way, as long as X is 1, it's going to count 0, 1, 2, 3, and then 0, 1, 2, 3, and so on. In next chapter, I'm going to give you more example for counters. They are not going to be very different from these ones, but it's the same idea. And X is going to be used. X is going to be used like if you want to run the counter or stop the counter. And at any time when X is 0, you are going to stay in the same state. So if X is 0 here, I'm gonna stop here. And then when X is 1, I'm gonna come from here to here. So you are gonna pause it in the exact count. When X is 1, you're gonna move to the next one and so on. Any questions? What is Y? So actually here, Y is giving you 1 when when it is 1, 1, before you move to from 1, 1, you are going to move to 0, 0 again, because this is how this counter is working. 0, 1, 2, 3, and then 0, 1, 2, 3. So after 1, 1 here, you are going to go to 0, 0. At this time, Y is 1. So Y is 1 only to tell you it is the state of 1, 1. Any questions? Okay. Now, I told you here I put the output here instead putting the output here on the arrows here for a reason. It's a very small thing, okay? It's not a big deal, but you need to know it, okay? What is this? Here I'm gonna make a definition. The sequential circuits, I'm gonna divide the sequential circuit into two types. One type, we call it mealy machine or Moore machine, okay? By the way, maybe this term is going to confuse some students because this is the term I used in the lab. Usually synchronous sequential circuit, and when I say synchronous means we use a clock, same clock, okay? That's how we can make synchronization. Usually, guys, if you have a big circuit, Usually you have only one clock that control all of them. If it is big circuit, this is how we can make synchronization. You get what I'm saying? So anyway, so any synchronous sequential circuit, which is almost everything I explained in this chapter, sometimes you call it finite state machine or FSM, just a different name. Okay, because you can see we have states and we can move from one state to another, just a different name. So in lab I use the term finite state machine, so that means it's synchronous sequential circuits. You get what I'm saying? Because you have a state, you move from one state to another. Anyway, so this circuit, they have two types. One type I call it merely, the other type we call it Moore. Okay, there is a small difference between them. Look at the difference here. The difference is that how you are gonna get the output. If I get the output directly from the flip-flops, so this is the flip-flops. If I get the output only from the flip-flop, not from the input, so the input is not involved at all here, that's what we call Moore machine, right? But if I get the output from this one is the flip-flops, okay? I'm gonna talk about registers. You will see register is just a number of flip-flops. I call them register. So anyway, so it's the flip-flop, okay? So here, it depends how you are going to get the output. If I get the output only from the flip-flops, I'm going to call it Moore. This type is Moore. If I get the output from the flip-flops and the input as well, that's what we call it merely. Just a definition. It's not a big deal. For example, in this circuit here, if you look here, this one, I get the output here. Why? I get it from flip-flops. Input here, input is already here. Also, flip-flops are coming here. Look here, I use it here also flip-flops, okay? And this one is coming here. So the output here, to get the output here, the input is involved. Because it's involved in the input, we call it mainly, okay? In case of Moore, this is the last circuit we have. In case of Moore, the input, I'm gonna get the output only from flip-flops. No, the input is not gonna contribute directly to the output. You get what I'm saying? This is a small difference, okay? Just to differentiate between the two types, okay? So, and again, that's not a big deal, but anyway, to differentiate between the two types is, if it is Moore, I'm gonna put the output here. So if I put the output here, put the output here, just I'm telling you this output is coming from the state, only the state. It has nothing to do with the input. You get what I'm saying? This one, the output is coming from, just to tell you this is Moore. If I put it here, that means it's coming from the state and also the input, because I put it here next. If you put the output next to the input, so I'm telling you the input is gonna, output is coming also from the input and the state, okay? Anyway, that's a small difference to tell you between Moore and merely. Just a definition, it's not a big deal. Any questions? So in the coming lab, nothing, if you just understand this lecture, everything will be okay. It just, I recommend, and that's what I made a video. You should start with this example. You should understand it. The coming lab, it's exactly similar to this example. But it's much easier. So instead of having two inputs, I just cancel this one, and we have only one input here. Any questions? We still have 2 minutes. Okay. Any questions? Okay. Now, so what is left in this chapter? Okay. In this chapter, two things are left. Okay. The first, what I did so far, guys, is I give you a circuit. Listen to me. What I did so far, I give you a circuit, and then we analyzed the circuit in order to get the state diagram, state table, and the state diagram. Is that okay? Okay. What about the opposite? If I want to make a design, if I want to design a circuit, so I'm gonna say I want a circuit that has this state diagram. Can you get the circuit? Yes, we are gonna do that. So I'm gonna say, for example, I need a circuit given this state diagram. How can you design the circuit? The opposite. So this is the last section here. I'm gonna explain. So so this is the last part here. Yeah, here. Design. How can you design? So here in this one, I'm gonna give you a certain state diagram. I wanna, here you have only one flip, you have here two flip-flop because you have 4 states, and then I want the circuit to behave this way. I want the circuit to behave this way. Can you make the circuit? So it's not difficult. It's very easy. But anyway, this is the part. The second part here, which is also very easy, we call it state reduction. What state reduction means? Okay, you remember the key maps? Key maps. What did we do in the key maps? Okay, if you have a function, I can simplify this function so that the two functions give me exactly same output. It's the same thing here. How I can do something like key maps, it's for sure it's completely different than what we did before, but it's the same thing. How can I do reduction? How I can minimize it so that the two diagrams are going to do exactly same thing. That's why, for example, here I'm going to explain it next time. But just this is only the two parties we have. So for example, I'm gonna next time I'm gonna brief you to use this one, which is more complicated. This one is more complicated than this one, but they are equivalent. They are the same. They give the same results. So I'm gonna give you one, and then how can you simplify it? Simplify means there are some redundant states you can just remove. I'm gonna explain it next time. So it's very easy. Similar to the key maps, but it's key maps is more complicated than this one. This one is just pretty simple, okay? But again, these two are equivalent, okay? Anyway.